Okay, as we continue, you have to take note that the tangential deviation of C with respect to A is positive based on the result of our computation. So that means that C is above the reference tangent at point A, so as expected. So we are going now to compute for the slope angle at point A. So the slope angle at point A, which is denoted by theta A, based on our illustration. So this will be our theta A. So that theta A will be equivalent to tangential deviation. This angle is equal to this opposite side over the adjacent side. So tangential deviation of point C with respect to A all over AC. So if we try to substitute the values here, we have the result of tangential deviation of point C with respect to A, which is 0.019531. Divide to the length of this from point A to point C is 3. So we can have the result, which is 6.510 times 10 to the negative 3 radian, or this can be, or that is 0.373 degrees, and that is in a clockwise direction. So the second part is to compute for the displacement at point D. So we have here the displacement at point D. So what is the equivalent value for that? So that is this displacement at point D. So the second part is to compute for this displacement at point D. So we have to compute first for the tangential deviation at point D. So we're going to have here tangential deviation at point D with respect to A is equal to area of the moment diagram all over EI, that is from A to D, multiplied to bar x of D, which is our reference point. So therefore, if we try to get the area of the bending moment diagram, so we have only from point A to point D. So that is from point A to point D. So we simply have to get first from our diagram. We have here our diagram. So this is 300 and this is point D. So first from that distance is 1/3. So we simply have to get this unknown value. So this is, it has 1 meters and this one is 3 meters. So therefore, if we're going to have this value, let us call this as our y. So y all over 1 is equal to 300 all over 3. So simplifying, you have 300 all over 3. So it gives us a value of y, which is 100. So therefore, the area of this from point A to point D is equivalent to one half of 100 times 1 times its distance from this centroid towards point D is 1/3 of 1. So, and this is all over EI, so we have 1 all over 20 times 10, 20. This is 1 over 20.48 times 10 to the third. So if we try to simplify this one, we get a value of 0.8138 times 10 to the negative 3, or this is equivalent to 5.696 times 10 to the negative 3 meters, or 5.70 mm, and this is downward. So we have now the value for the displacement of our displacement at point D for our beam. Example number 3 is determine the value of EI small delta at end D of the overhanging beam. So we are given with our load diagram. So we try to choose our point C be our fixed support. So that will be our reference point as we draw our bending moment diagram. So therefore, if we have that as our fixed support at point C, so we only have here 3 loads. You only have load R sub A, which is 78. Then we have our 150, and we have our 30. So we try to draw now our bending moment diagram. So that will be 78 times 10, so 780. Then we have a downward load 150 times 6, that is 900. So this is 780. Then we have 900, so negative 900. Then we have 30 times 4, so 120. So we have here negative 120. So we have now our bending moment diagram. So we try to draw our elastic curve. So if we draw our elastic curve, we have here from that portion, then it will go up. So this is our elastic curve A, and this is point D. It goes up because we have here at point C, we have an upward concentrated load. So if we try to draw here our tangent line, so we draw our tangent line. So therefore, from this is our actually our theta C. This is also our theta C. And this one is the displacement at point D, and this portion is the tangential deviation at point D with respect to C. And this one is the tangential deviation at point A with respect to C. So we can now identify our tangential deviation with respect to A. So we will have here the tangential deviation of A. So we'll have EI tangential deviation, or we can have here tangential deviation at of point A with respect to C is equal to area of moment diagram all over EI, then from point A to C, that is times the reference point, which is bar X of A. So if we try to have this, we don't have a value for EI, so we can rewrite this as EI tangential deviation of A with respect to C is equal to the area. Let us identify the area. You have 2 area of the triangle from point A towards point C. So we have here 1/2 positive direction, 1/2 times 780 times the length, which is 10, times its moment arm distance from from the centroid towards our reference point, which is point A. So that is the moment arm distance, that is equivalent to 2/3 of 10. Then we have a downward, so this will be minus 1/2 times 900 times 6 times distance from that centroid towards point A. So that will be 4 plus 2 all over 3, 2/3 of 6. So if we try to simplify, this will give us 4,400 pounds feet cube. So we have now our value for tangential EI tangential deviation of A with respect to C. So therefore, our theta C is equal to the tangential deviation at point A with respect to C all over segment AC. So this will be this one. So this is equivalent to 4,400 all over 10. So we have the result, which is 440 pounds feet squared. So we have now our value for our theta C. So now we can have the tangential deviation of point D with respect to C. So therefore, our tangential deviation EI, tangential deviation of D with respect to C, is equal to area of the moment diagram over the moment diagram, then from C to D times x bar x of D. So our reference point is at point D. So therefore, based on our bending moment diagram, we only have one triangle, so one figure, so that will be equivalent, which is which is below the x-axis, so that is downward, -1/2 times 120 times its distance, its length, which is 4, times the distance from the centroid of the triangle towards point D. So that will be, because this is our reference point, it's at point D, so the moment time distance is 2/3 of 4. So if we try to simplify, you have -640 pounds cubic feet. So therefore, if we have our displacement at point D will be equivalent to theta C, slope angle at point C, times segment CD minus the tangential deviation of point D with respect to C. So that is equivalent to, you can have here EI, the displacement at point D is 440. This is the equivalent value for our theta C times our segment CD, which has a length of 4, minus 640. So we have the value of 1,120 pounds cubic feet. So we have now our, this is upward. So we have now our, this is positive, so that is upward. So we have now the value for our displacement EI. Actually, this is EI, the displacement at point D, since we don't have a value for our flexural rigidity EI. So this is our final answer.